Good morning. Today we are going to start the chapter Distribution Law. It is observed that when a solute is added to a mixture of two immiscible liquids, in both of which it dissolves, then it distributes itself between both the liquid in such a way that the ratio of concentration of the solute in both the liquid remain constant at a constant temperature. These observations were made by Berthold and Junglish by dissolving iodine to a mixture of carbon disulfide and water. Nernst, however, showed that the ratio of concentration is constant only when the solute has same molecular mass in both the solvents. That is, the solute neither undergoes association nor dissociation in both these solvents. The generalization put forward by Nernst is called Nernst distribution law, and it is stated as a solute distributes itself between two non-miscible solvents in contact with each other in such a way that at equilibrium the ratio of the concentrations of the solute in the two layers is constant at a given temperature, provided the molecular state of solute is same in both the solvents. If a solute X distributes itself between solvents A and B, the distribution law is written as concentration of X in solvent A upon concentration of X in solvent B is equals to K. The constant K is termed as the partition coefficient or distribution coefficient. Experimental verification of distribution law. Solutions of iodine in carbon disulfide of different concentration are shaken with water. Taken in different bottle, a known volume of each layer is piped out and titrated against sodium thiosulfate solution, and the concentration of iodine is determined. Similar experiment can be done by dissolving succinic acid to a mixture of ether and water. The resultant will ratio C1 upon C2 is almost constant, hence the distribution law is valid in this case. Now, conditions for validity of distribution law. First, the essential conditions for validity of distribution law are: first, constant temperature; second, the two liquids are immiscible or partially miscible; 3. The solutions are dilute; fourth, the molecular state of solute is same in both the solvents, that is, the solute does not undergo association or dissociation in any of the solvents. This law is not valid for distribution of phenol in ether and water because phenol undergo association to form dimers in chloroform. Similarly, the law does not hold for distribution of benzoic acid in benzene and water because benzoic acid exists as dimer in benzene. Thermodynamic derivation of the distribution law. The principle underlying the derivation of distribution law from thermodynamics is that in a phase equilibrium established between two immiscible liquids, the chemical potential of the solute must be same in both the phases. Suppose a solute is present in two immiscible solvents, A and B, in contact with each other. Suppose further that its chemical potential in solvent A is nu A and in solvent B is nu B. When two phases are in equilibrium, their chemical potential will be equal to one another. That is, nu A is equals to nu B. From thermodynamics, we know chemical potential of a substance is given as nu is equals to nu naught plus RT ln A, where nu naught is the standard chemical potential and A is the activity of the solute in solution. Therefore, nu A is equals to nu naught A plus RT ln A for phase 1, and for phase B it is nu B is equals to nu naught B plus RT ln A of B, and hence nu A naught plus RT ln A is equals to nu naught B plus RT ln AB. RT ln A upon RT ln AB is equals to nu B naught minus nu naught A. ln A upon ln A of B is equals to nu naught B minus nu naught A upon RT. Now at constant temperature, the standard chemical potential nu naught A and nu naught B are constant. Since R is also constant, it follows that ln A of A and A of B is equals to constant, and since the solutions are dilute, therefore the activities are equal to concentration. So equation becomes concentration of A upon concentration of B is equals to constant. This is the Nernst distribution law. Modification of distribution law with change in molecular state of solute. Nernst showed that the ratio is constant only when the solute has same molecular conditions in both the liquids. That means the solute does not undergo association or dissociation in any of the liquids. However, if any of such changes take place in one or both the liquids, then the distribution law gets modified. Let us consider cases in which a solute may associate or dissociate or enter into chemical combination with one of the solvents. Association of solute in one of the solvent. Let X represent the molecular formula of solute and let it remain normal in phase 1, in which its concentration is C1. Assume that the solute undergo association to form molecules Xn in phase 2. Let the C2 be the concentration of the solute in phase 2. There are two simultaneous equilibria existing, phase 1 and phase 2, and Nx Xn, phase 1 and phase 2. Let alpha be the degree of association of solute in phase 2. Then the concentration of associated molecule in phase 2 is 1 upon n C2 alpha. The concentration of normal molecule in phase 2 is 1 minus alpha C2. Applying law of equilibrium to equilibrium equation first, we can write concentration of X in phase 1 upon concentration of normal molecules of X in phase 2 is equals to constant, or C1 upon 1 minus alpha whole C2 is equals to constant. Applying law of equilibrium to equilibrium second, we can write concentration of associated molecule in phase 1 upon concentration of normal molecule in phase 2 raised to power n is equals to constant, or 1 by n C2 alpha upon 1 minus alpha whole C2 raised to power n is equals to constant, or n cube root n root C2 alpha upon 1 minus alpha C2 is equals to constant. Dividing equation 1 and 2 by equation 2, we get C1 upon C2 alpha raised to power 1 by n is equals to constant. However, when the molecules of the phase 2 are completely associated, that is alpha is equals to 1, then equation became C2 upon C2 raised to power 1 by n, which is equals to constant. Equation 4 has been checked by studying the distribution of benzoic acid between water and benzene. The acid exists almost entirely as dimer in benzene but in normal state in water. Dissociation of the solute in one of the solvents. Dissociation of the solute in one of the solvents. Let the solute X dissolve in phase 1 in its normal state and undergoes dissociation in phase 2 as shown. The concentration of X in phase 1 is equals to C1 and concentration of X in phase 2 is equals to C2. Let alpha be the degree of dissociation of solute in phase 2. Then the concentration of normal molecule in phase 2 is equals to 1 minus alpha C2. The two equilibria existing are XX phase 1 and phase 2. X is equals to gives and forward and backward A plus B, that is phase 1 and phase 2. Applying distribution law to equilibrium first, we get C1 upon C2 whole 1 minus alpha is equals to K, that is distribution constant. Further, if the solute undergoes dissociation in both the phases, then distribution law gets modified as C1 raised to power 1 minus C1 whole 1 minus alpha upon C2 1 minus alpha is equals to K. The solute enters into chemical combination with one of the liquids. When the solute enters into chemical combination with one of the solvents, there is no change in general equation of the distribution law. Let C1 be the concentration of the solute, X remain in the normal state in the phase 1, and C2 its total concentration when it enters into chemical combination with the second solvent in phase 2. The equilibria existing are XX, X plus NS, X, NS, phase 1, phase 2. If alpha is the fraction of the solute that enters into chemical combination with the solvent, then the concentration of various species is as follows. Concentration of normal solute molecules C2 whole 1 minus alpha. Concentration of combined molecules formed C2 alpha. Applying the law of chemical equilibrium to the equilibrium second, we get K is equals to C2 alpha upon C2 whole 1 minus alpha solvent raised to power n. Since the solvent is in large excess, its concentration may be taken as constant. So C2 alpha upon C2 raised whole 1 minus alpha is constant. Since the distribution law is valid only for concentration of similar species, that is single molecule of X in both the phases, hence applying the law of equilibrium to law to equilibrium first, we have C1 upon C2 whole 1 minus alpha is equals to constant. Dividing equation third by equation second, we have C1 upon C2 alpha is equals to constant. Now alpha, the fraction of the solute that combines with the same solvent, is also constant at given temperature. Equation third may be written as C1 upon C2 is equals to constant. Thus, combination of the solute with one of the solvents does not make any change in the fundamental equation of distribution law, except in changing the numerical value of the partition coefficient. Applications of distribution law. First, in calculating the solubility of a solute in a solvent, the solute added to two immiscible liquids forms saturated solution with each liquid. Therefore, the concentration as equilibrium are equal to the solubility of solute in both liquids. C1 upon C2 is equals to S1 upon S2 is equals to K. K is distribution constant. C1 is equals to C2. C1 is equals to S1 is the solubility of solute in liquid 1, and C2 is equals to S2, the solubility of solute in liquid 2. Knowing K and solubility in one of the liquids, its solubility in other liquid can be determined. Study of association or dissociation of a solute. As shown above, if the solute associate in one of the solvent in which its concentration is C2 but not in other in which its concentration is C1, then C1 upon C2 raised to power 1 by n is equals to constant. N is a simple number and can be determined by hit and trial method. The values of C1 and C2 obtained in the experiment are put in equation first, then putting n is equals to 2, 3, 4 and etc. The corresponding values of K are calculated, and the number which gives a constant value for K is the correct value of n. Second method is logarithmic method. We have the equation C1 upon C2 raised to power 1 by n is equals to K. Then taking log on both sides, we get log C1 is equals to 1 by n log C2 plus log K. The two experimental values C1, C2 and C1 dash C2 dash, we can write C log C1 is equals to 1 by n log C2 plus log K, and log C1 dash is equals to 1 by n log C2 dash plus log K. On subtracting equation second from equation first, we have log C1 minus log C1 dash is equals to 1 by n raised to power 1 by n whole log C2 minus log C2 dash, or we can say n is equals to log C2 minus log C2 dash upon log C1 minus log C1 dash. Hence n can be calculated. Similarly, when a solute undergoes dissociation in one of the solvent in which its concentration is C2 but not in the other in which its concentration is C1, then C1 upon C2 whole 1 minus alpha is equals to K. Thus, if The degree of dissociation of the solute is known at one concentration. Its value at any other concentration can be obtained since K is constant. Distribution indicators. It is common observation that iodine distributes itself considerably more in carbon disulfide than in water when both the solvents are in contact with each other. Therefore, an extremely dilute solution of iodine in water can be successfully titrated by adding a drop or two of carbon disulfide. The concentration in the carbon disulfide layer becomes large enough to give a distinct violet colors. Fourth, discrimination of degree of hydrolysis and hydrolysis constant of aniline hydrochloride. Aniline hydrochloride is a salt of weak base aniline and a strong acid HCl. Its degree of hydrolysis is determined as follows. Determination of hydrolysis constant. A known mass of aniline hydrochloride is dissolved in dilute hydrochloric acid of known molarity. A known volume of benzene is added to it and a mixture is shaken till the equilibrium is attained. On standing, the mixture separates into two layers. The hydrolysis reaction of aniline hydrochloride is unhydrolyzed salts reaction with water give free base and acid set free. The aniline hydrochloric salt will be present in two forms, namely unhydrolyzed salt and second is hydrolyzed salt, and the hydrolysis constant is given as Kh is equals to C6H5NH2 concentration and concentration of H3O positive upon concentration of C6H5NH3 positive. A known volume of benzene solution is withdrawn and analyzed for base and is found to contain alanine. Study of complex ions. The following reaction involving formation of complex ion Ki plus I2 gives Ki3 and some more. Distribution law has been applied in determining the formula of the complex ions I3 negative and Br3. The following example will illustrate the method. A solution of iodine in carbon disulfide is shaken with water and distribution coefficient is calculated. A solution of iodine in CS2 of known concentration X is shaken with aqueous solution of Ki of known concentration. Third, after the equilibrium is established between the two layers, the concentration of iodine left in CS2 layer is determined volumetrically by titrating against standard hypo sodium thiosulfate solution. The total concentration of iodine in aqueous layer will be much higher due to the formation of soluble complexes Ki3. In the process of extraction, the most important application of the distribution law is the process of extraction in the laboratory as well as in industry. In the laboratory, for instance, it is frequently used for the removal of dissolved organic substance from aqueous solution with solvents such as benzene, ether, chloroform, carbon tetrachloride, etc. The advantage is taken of the fact that the partition coefficient of most of the organic compounds is very largely in favor of organic solvents. We can derive a general formula which enables the calculation of the amount that is left unextracted after a given number of operations. Let V mole of the solution containing W gram of solute repeatedly extracted with small v ml of another solvent which is immiscible with the first. Let W1 be the mass of the solute that remain unextracted at the end of the first operation. Then Kd will be given by W1 upon V upon W minus small w1 upon small v, or we can say small w1 is equals to w kdv upon kdv plus small v. Similarly, at the end of second extraction, the amount w2 small w2 that remains unextracted is given by w kdv upon kdv plus small v raised to power whole twice. In general, the amount that remains unextracted at the end of n operations Wn will be given by W kdV upon kdV plus V whole raised to power n. It is evident that in order to make Wn as small as possible for a given value of kd, n should be as large possible. But n into V is equal to the total volume of extracting liquid available. That is, it is constant. Therefore, it is better to keep n large and V small rather than the reverse. In other words, the efficiency of extraction increases by increasing the number of extraction using only a small amount of extracting solvent each time. For the same reason, in the washing of precipitates, it is more effective to use a small quantity of other at a time and to repeat the process of number of times. The same principle applies in the desilverization of lead by Parquet's process. The argentiferous lead is melted when heated to 800 degrees Celsius. Molten zinc is then added. Molten lead and molten zinc behave as a two immiscible liquid in contact with each other, and silver behaves as a solute which is more soluble in zinc than in lead, and the partition coefficient being of the order of 300 at 800 degrees Celsius. Silver therefore passes radially from the heavier lead layer to the lighter zinc layer, which is separated. By repeating the process 3 or 4 times, almost the entire amount of silver passes into the zinc layer, and we get the lead. That's it for the chapter. Thank you.